Hello everyone, I'm Brooke and I'll be facilitating today. A couple of notes before we get started. We have a full house. Lots of traffic professionals are here, including engineers and consultants. Thanks for showing up. Not everyone is eager to learn about revolutionary technology, so pat yourself on the back. You're joined today by multiple people who care about empowering the traffic industry with new tools. We hope you get something of value. You know the drill. We'll be muting everyone to minimize background noise through the presentation. Today we have Dan Cook. Dan is a senior configuration engineer at Rhythm Engineering, which means he helps design and configure signal optimization for NSYNC. He also provides expert training and ongoing support for dozens of deployments, working with government agencies and contractors, traffic engineers, signal supervisors, and signal technicians. He has implemented NSYNC with several state DOTs, in addition to numerous cities and counties, managing deployments in Arizona, California, Georgia, Kansas, Missouri, Pennsylvania, and Virginia, to name a few. Dan's research interests include transportation safety, predictive crash modeling, and intelligent transportation systems, with specific focus on adaptive signal optimization. Dan holds a master's degree in civil engineering with a transportation emphasis from Iowa State University. Lastly, we love questions. You can type any questions you have by opening the Q&A window located to the bottom right of your screen. Following the presentation, Dan will take time to address these questions, so make sure to send us yours as we go through the presentation. Again, thank you for joining us and enjoy the presentation. Dan, welcome.
Thank you for everybody tuning in today for this webinar. And also thanks to our outstanding marketing team for bringing this presentation to you. The information covered in this webinar is from a recent report offered on our website called How to Solve the 15 Toughest Traffic Management Challenges with NSYNC Adaptive Traffic Signal Control. It talks about how to configure NSYNC for specific applications. It's available for download at rhythmtraffic.com/research. This is a list of the 15 different traffic challenges and applications covered in the report. Each one includes details on how to configure NSYNC along with real-world examples. Today, we are going to focus on 5 of those applications: intersecting arterials, emergency vehicle and railroad preemption, events, shopping centers and high-volume variations, freeway interchanges, and flashing yellow left turn arrows. Let me first talk a little bit about NSYNC. NSYNC was first deployed in early 2008 and is now trusted to manage traffic at nearly 1,000 intersections in 25 states, with more added every month. We are very excited about what this traffic management tool can do for public agencies. Simply stated, NSYNC automates traffic signal optimization and synchronization. You will notice a reduction in complaint calls, enjoy not having to recreate timing plans every couple of years, and delay the need for costly road construction. NSYNC dramatically improves traffic. These results are proven through many independent studies available on our website. NSYNC's real-time adaptability is what makes NSYNC different. Signals communicate with each other via tunnel messages so downstream intersections know when to expect platoons to arrive. Each intersection continuously monitors queue and wait time on all phases to dynamically allocate green time to adequately serve the intersection's demand. NSYNC does not use a ring structure, so it is free to pick the appropriate phase sequence to best serve demand at the intersection. Some of you tuning in today may already have NSYNC. For those that are unfamiliar with NSYNC's operation, let me spend a few minutes explaining NSYNC's logic. This is a time-space diagram showing the relationship between tunnels and space-time. Distance along the corridor is represented in feet on the horizontal axis. Time in seconds is represented on the vertical axis. The vertical lines are intersections on the corridor. The orange and green bands stretching across the diagram are tunnels. Tunnels achieve synchronization between signals by guaranteeing green time for a platoon in the tunnel. In this example, the orange tunnel represents eastbound traffic and the green is westbound traffic. The period length is simply the duration of time from the start of one tunnel to the start of that same tunnel later in time. The global optimizer tells the intersections when these platoons will be arriving, while the local optimizer at each intersection dynamically schedules green time for all movements based on queue length and wait time. There are two rules to InSync's operation. The first rule is each tunnel must be served once within a period. The second rule is all phases with demand must be served at least once within a period. InSync may reservice movements within one period length. Tunnels can start early, extend past the end of the tunnel time, and truncate early based on the demand of the platoon. Central Sync is your user interface to adjust InSync's adaptive configurations. No license is needed to run Central Sync with your InSync system, and you can install it on as many computers as necessary. The ability to access and edit InSync's adaptive configurations is very easy and fast, but at the same time is password protected for your security. Most of the InSync graphics used in this presentation originate from Central Sync. Please visit Rhythm Engineering's YouTube channel to access Central Sync tutorial videos and learn how easy it is to work inside the InSync environment. Let us dive right into our first challenge, intersecting arterials. There's a variety of crossing arterials on our roadways. The objective may differ depending on the traffic patterns. You may want all four through phases to progress traffic through the crossing intersection, or you may want to have left turning traffic from the main line progress through downstream signals on another arterial. The first thing you need to do is define the objective of the intersecting arterials. For this example, our objective is to provide progression on all four through phases. In Central Sync, you will first configure the tunnels on the main direction, which in this case is north and south. The white space in between the southbound and northbound tunnels is where you want the east and westbound tunnels to occur. So, the next step in Central Sync is to configure tunnels on the crossing arterial, such that the occurrence of these east and west tunnels are during the non-north-south tunnel durations. You will need to set local offsets under east and westbound tunnels at all intersections on the crossing arterial to allow these two tunnels to pass through the crossing point during the non-north-south tunnel durations. Columbia County, Georgia uses InSync on a large section of their roadway network. The intersections shown here are a smaller chunk of their network and are configured to operate as a crossing arterial. Both arterials have an ADT of over 40,000 vehicles per day. The adjacent land use is heavily retail. The objective was to coordinate all four through phases. Elsewhere on the network, mainline left turns are coordinated onto other intersecting arterials. A study conducted on Washington Road in Columbia County, Georgia, showed InSync reduced stops by 77%, travel time by 34%, delay by 81%, emissions by 23%, increased average speed by 40%, and reduced fuel usage by 17%. The second challenge we are going to discuss is how InSync handles railroad and emergency vehicle preemptions. While preemptions may disrupt traffic flow, they are important in order to clear railroad tracks ahead of a train's arrival and to get emergency vehicles to their destinations quickly and safely. But when the preempts are over, we can get stuck with long queues and frustrated drivers. InSync will detect the presence of a preemption. A rhythm intercept module may be required to listen for the preemption call, but at no point does InSync actually intercept and pass the preemption signal. The controller at this point will override InSync's operation. InSync will stop placing calls to the controller, but continue to run its dynamic schedule in the background. After the preemption, InSync will place detector calls to the controller to allow the controller to cycle through phases in order to clear long queues or demand with high wait time. Once InSync's adaptive schedule matches the controller's operation, InSync will resume control of the intersection. This process speeds up clearing queues while getting the intersection in sync with the rest of the corridor as quick as possible. All of this is possible without the need to place the corridor in transition. Claremore, Oklahoma runs InSync in close proximity to railroad tracks. The intersections receive frequent railroad preempts throughout the day. InSync smooths out the effect of these trains by clearing long queues and getting the affected intersections back in step with the rest of the InSync corridor. In South Carolina, Mount Pleasant's InSync system on US 17 experiences frequent emergency vehicle preempts as a result of a nearby hospital. US 17 is an award-winning corridor with an independent study showing InSync's ability to reduce stops by 50 to 67%. Another challenge we face is how to handle corridors with variable flow rates. These may be from scheduled events from a large generator, such as a sporting event, unexpected queues from shopping centers, and corridors with very heavy and variable mainline volumes. Configuring InSync to handle event traffic is a simple task. First, you need to set up a configuration of SimpliSync that handles the event traffic patterns. In this example, a configuration was created for traffic entering a sporting event and another configuration for traffic leaving the event. Lastly, use a specific event schedule to set a start and end time for these configurations. Side street queues from shopping centers will fluctuate throughout the day. Create large gaps between the tunnels so that green time can be allocated when needed. During times of lower demand, InSync will reallocate the green time elsewhere during the period. Some corridors are plagued by high volumes on the main line that can fluctuate throughout the day. For this situation, configure InSync with a high period length and large tunnels in order to capture the very large platoons that will travel through the corridor. During times of smaller platoons, the InSync local optimizer will truncate the tunnel and reallocate the unused tunnel time elsewhere at the intersection. Columbia, Missouri is home to the University of Missouri. InSync on Grindstone Parkway serves as a route for football game day traffic. Event configurations were created to run during explicit time periods that correlate with the football games. InSync on South Jordan Creek Parkway in West Des Moines, Iowa, serves as a regional mall and big box retailers. The configuration was set up to handle variable demand as a result of the retail use, including handling Black Friday traffic. An award-winning corridor run in InSync in Upper Marion Township, Pennsylvania, handles high mainline volumes, which are also variable due to the close proximity of the largest mall in the United States. Results show the positive improvement InSync has on this corridor. Incorporating freeway interchanges into a network of signals is another challenge, mainly because of the differing geometric conditions and complex traffic patterns. Freeway interchanges is such a broad topic, so I am narrowing down our discussion to diamond interchanges. The first type of diamond interchange we will explore consists of two independent operating ramp terminals. It is critical to consider ramp spacing, lane storage, and traffic flow. You may need to adjust local tunnel durations and local tunnel offsets to accomplish integrating the interchange into the larger InSync corridor. This first scenario is a diamond interchange with independently operating ramp terminals. The mainline left turns are very heavy and the ramp terminals are closely spaced. The combination of the traffic pattern and geometries results in spillover. It is best to configure the InSync tunnels to not overlap so that the left turn can be serviced with its adjacent tunnel. In this example, the left turn onto the I-27 southbound ramp will get serviced concurrently with its adjacent tunnel, which is the green-colored tunnel. The orange-colored tunnel occurs right after the green tunnel. Then, the left turn onto the I-27 northbound ramp will lag after the green tunnel and concurrently with the orange tunnel. This eliminates the spillback by serving the left turn while the platoon is flowing through the interchange. The next scenario is also a diamond interchange with independently operating ramp terminals. The I-27 northbound off-ramp is extremely heavy and the ramp terminals are closely spaced. The combination of the traffic pattern and geometries results in major backups, and it is best to configure the InSync tunnel to start early at the downstream ramp terminal. In this example, you can see how the green tunnel starts much earlier at the I-27 southbound ramp. This will encapsulate the heavy off-ramp traffic into the green tunnel and still accommodate the platoon traveling through the interchange. Heavy off-ramp traffic may lead to other issues, such as the ramp itself not being long enough to store the queue without spilling back onto the freeway. In this situation, it is best to configure the InSync tunnels such that two side street gaps occur within one period. If you look at the Central Sync tunnel configuration, there are two opportunities to serve the ramp within one period. Doubling the frequency of serving the ramp will reduce the queue lengths and help eliminate spillback onto the freeway. A four-phase diamond is a unique type of diamond interchange where all four phases are either served in a clockwise or counterclockwise rotation around the interchange. This example with InSync shows how to configure the InSync tunnels to work with a clockwise four-phase diamond. Configure the tunnels such that two side street gaps occur within one period. These two gaps are where the southbound and northbound ramps will be served. The divergent diamond interchange is a specialized diamond interchange that crosses through traffic onto the left side of the roadway. InSync views this as one intersection. It is necessary to configure the tunnels such that a gap occurs in between opposing tunnels. The gap needs to be large enough for the first platoon to clear the second crossover point, plus the amber and red time before the opposing platoon arrives at the interchange. Flashing yellow turn arrows is our last topic of conversation today. Flashing yellow turn arrows is not a challenge, but rather an innovation that helps us overcome challenges with arterial coordination. Most importantly, the flashing yellow arrow eliminates the yellow trap, allowing lagging left turns and still having the permissive left turn state. It is important to note that the controller drives the flashing yellow arrow operation and InSync schedules time appropriately with the knowledge that a flashing yellow arrow exists. All we need to do in Central Sync is select flashing yellow as the type of left turn operation. To expand on why lagging lefts improve the efficiency of arterial coordination, this graphic shows how InSync allocates screen time if left turns are laggable or if left turns are not laggable. As you can see, there is more flexibility with lagging left sequences because you do not need to use the non-tunnel time to serve the mainline left turns. InSync will also work with flash and yellow arrow applications where the flash and yellow is suppressed when a conflicting pedestrian movement is running. Hillsboro, Oregon utilizes this controller feature. Thank you to everybody for joining today's webinar. Visit rhythmtraffic.com to learn more about everything InSync related. We will now be taking questions.
Thank you so much, Dan. We will now go ahead and address the questions posed by today's attendees. Our first question is, how many crossing arterials can you have in one InSync network?
You can configure as many crossing arterials as you need to. There's not a limit to the amount of intersections nor the limit to the amount of crossing arterials you can include in the InSync network.
How big can an InSync network be configured?
There's really no limit to how large the InSync network can be configured.
Okay, what is the maximum ADT that InSync is currently operating on?
I believe the largest ADT, mainline ADT that InSync operates is somewhere around 70,000 vehicles per day. But of course, that all depends on the amount of capacity that's on the arterial.
Okay. How does InSync handle Black Friday traffic with it being shopping traffic at an odd time?
Well, there's a couple things that can happen. For one, like in West Des Moines, Iowa, where we just talked about, the configuration that runs there was able to absorb all the traffic from the mall and all the big box retailers. However, in certain areas, it may be necessary to set up a specific event configuration where you need to offer more time to the side streets, and then the engineer can go in CentralSync and specify at what time should the specific event start and end. So you can have that event end on Black Friday whenever they expect traffic to resume back to normal.
How is the InSync period determined, and how are the sequences as well?
The InSync period is determined first by just looking at the geometry of the corridor. Obviously, it depends on the goal, but mainly the goal of InSync is to provide two-way progression on the arterial. So what we're looking at is, depending on the intersection spacing, we need to have good starting points at the beginning of the corridor to build a platoon, but then also as the platoons flow through the corridor both ways, there needs to be still adequate side street time available between the tunnels, as you can visualize on the time-space diagram. Then, then we check the volumes and make sure that the tunnels are large enough to handle the volumes depending on the time of day, as well as the non-tunnel time is long enough to also handle all of the non-tunnel phases. I think there was a second part to that question about sequences though, right?
Yes, we were just asking how the sequences are determined as well.
Okay, so it depends on if you are allowed to have lagging lefts at the intersection. If you have protected permissive left turns, you always have to lead those left turns no matter what. So the sequence there is always leading left turns. However, at intersections where you can lead and lag or lag both left turns or lead and lag, you have a lot more opportunities. And so the optimizer, as far as selecting the sequence on the main line, is looking at how do the tunnels overlap at the intersection. Does one tunnel lead ahead of the other tunnel where it could lead the first tunnel's concurrent left turn and then lag the other tunnel's concurrent left turn? Or perhaps the tunnels perfectly overlap to where the optimizer could lead both left turns or lag both left turns. All the optimizer is looking at is utilizing the time the best it can within the period and still have enough time to provide adequate green time to all the other phases at the intersection.
Okay, how does InSync handle an interchange situation where both southbound and northbound off-ramp traffic is heavy and have a tendency to spill back onto main line?
Well, in that case, what you're going to want to do is operate it more closely to what a four-phase diamond would operate. So if this interchange is at assuming it's a diamond interchange with independently operated ramp terminals, you want to set up the tunnels in such a way that when you release one of the ramps, you need to be running your tunnel on the other ramp, on the same direction that the off-ramp traffic is traveling, and still provide enough time if you are trying to get the platoon that's on the main line through the interchange, enough time to build those in, just like what we talked about in our example. You'll have to do the same thing for the other direction as well.
Can InSync be used with the HAWK pedestrian crosswalk system?
Yes, it can. All it needs is a InSync processor and an InSync or Rhythm Engineering pedestrian intercept module. It's a fairly easy interface, and we actually have at MacDill Air Force Base a HAWK system that's integrated into an InSync network of 6 intersections.
How does InSync detect long delays or queues? Is it through video detection?
Mainly, InSync uses the video detection to look at queues and wait time. However, if you're using InSync Fusion, it's going to use secondary detection to confirm the presence of the vehicle, but it's still going to use the InSync video detection to count the cars in the queue.
How do you determine if a traffic problem is a capacity problem and not amenable to InSync?
Well, in that case, if you're configuring the corridor and you're just trying to give that movement as much green time as possible, and you're still not clearing the queue or the main line, then it's definitely a capacity problem. I mean, you can basically just look at the volumes, and if it's past your saturation flow rate, then yes, you're going to be above saturation, and it's a capacity issue.
What are the benefits of InSync for a closely spaced offset signalized intersection with no nearby signalized intersections, i.e. no coordination?
You're asking me what the benefit of putting InSync on closely spaced intersections that are not coordinated?
Correct.
Well, the benefit is going to be having the tunnel messages go between those intersections, and you're going to be providing coordination. The also benefit of InSync is InSync has the knowledge to be able to clear out queues ahead of the tunnel. So as you can configure it in such a way that if your intersections are very closely spaced, you can start a tunnel early enough at a downstream intersection before the platoon even arrives to flush as much traffic out of those closely spaced intersections as possible.
Do you use one controller to operate a diamond interchange or two different controllers? Most of the diamond interchanges with one single controller have at least 6 phases under regular time of day type of operation. Will InSync treat the interchange as 2 different intersections?
No, all we need is one InSync processor, and InSync will treat the interchange as one intersection, and it will just place the calls to each phase as necessary. Now, the overlaps or the offsets and the overlaps programmed in the controller will remain there. InSync won't drive those specific overlaps and offsets as needed in the diamond interchange, 4-phase diamond interchange.
Over what duration of time are the published benefits of InSync based?
I believe the farthest back is 2008, so 5 years.
Can you discuss the challenges of configuring InSync with a single point urban interchange?
Actually, working with a single point urban interchange works very well with InSync because the single point urban interchange eliminates the amount of states possible at an interchange, where you're only looking at 3 possible phase pairs, or as InSync calls it, states. So there's a lot more flexibility to how InSync operates a single point, and that's exactly the reason why I didn't include it in this presentation, is because it's really a simple interchange for InSync to interface with.
How often do you have to update InSync's configuration?
You may need to tweak tunnels here and there depending on, after you first deploy the product. However, you shouldn't need to make any changes unless you're looking at a corridor that all of a sudden there's 50% more traffic on the corridor than there used to be. Then new configurations will be required in order to provide the necessary benefit to the users.
How does one analyze and report existing conditions, LOS, with InSync? What software exists for public engineers and private consultants to analyze how things are working with InSync and determine how well things will work with growth or development?
InSync can interface with VSIM, piece of software or simulation software. We've done that a few times, and that's the benefit of doing that is you can obviously set up a really nice simulation, and then having the plugin to run InSync to monitor the traffic and control the lights. With VSIM, you can have nice reports showing total intersection delays, network delay, level of service. You can also change your volumes to meet, 30 years down the road to see how InSync will deal with traffic then.
Is there a hands-on training class given by Rhythm Engineering?
Our project engineers at Rhythm Engineering are always available to offer one-on-one webinars with your team. Really, they're on-demand webinars whenever you need them. We'll cover any topics that you want to cover. Typically, during a deployment, what we will do is before we go down there, we'll offer a Central Sync introduction webinar. It's about an hour. And then while we're on site for the adaptive turn-on, we'll sit down in a classroom setting with you and your team and actually walk through Central Sync and look at your corridor in Central Sync and actually show how you can make changes to the corridor and monitor the system. Past that point, of course, we're available to hop on a webinar to teach anything that needs to be covered. We also have Central Sync and InSync Web UI tutorial videos on Rhythm Engineering's YouTube channel that they're about 2-minute to 3-minute videos that really cover certain topics. They're really nice videos.
Does InSync change cycle time or period length automatically?
You can set up a configuration to have a dynamic period. The user will set the minimum and the maximum period or the range that the period can fluctuate in between. The global optimizer is continuously looking at how are individual intersections serving their queues, and if one intersection down the corridor says, hey, I need more time to clear my queues at the intersection, then the global optimizer will step up the period, of course working within the lower and upper bounds of that dynamic period range.
How reliable has video been for vehicle detection and counting in different lighting and weather conditions?
Obviously, rapidly changing weather conditions, whether you just have a downpour that all of a sudden drops down, you're going to have some video detection problems, as you would with most video detection pieces. You're also going to have if you have a span wire intersection, you might have vehicle occlusion because of the fact that you have to mount the video detection cameras on the poles at the corner of the intersection. So you have some really sharp angles that you're looking at the approaches where possibly a semi-truck could totally occlude a vehicle in a left turn lane, or there's nobody in that left turn lane, but the fact that that truck or vehicle is covering up the detection zone, InSync is detecting something in that lane. To combat that, we came out with InSync Fusion, which ties an existing detection, physics-based detection at the intersection, to be able to confirm or deny the presence of a vehicle, while the InSync camera still measures the queue in each lane.
Dan, can you talk about InSync fog mode?
Yeah, so when you're running video detection, as well as InSync Fusion, there's a fog mode will kick in if the visibility on that camera decreases. And what it's looking for is areas of contrast. When the detection zones are initially set up, the user will set up fog zones. We recommend setting up 2 or more fog zones, and you draw those around areas of high contrast, where under normal light conditions, you would see contrast, whether it's a stop sign or a signal post or something in the distance. Now, if conditions deteriorate, whether you have fog or really heavy rain, if InSync sees that it can't see those areas of contrast anymore, it's going to drop into fog mode. And what the fog mode does, it will use historical green time to schedule time for that movement, because InSync's thinking, I can't use this data because I don't think it's reliable anymore, because I'm not able to see the areas in my view that I used to be able to see.
Can your system operate with existing loop detectors or any other detector?
Yes, it can.
Will Rhythm Engineering produce a tutorial CD?
I'm not sure if that's in the works, but I do know that all the tutorial videos that are out on YouTube will be placed in a special place on the Rhythm Engineering website, where we will call the video training library. But right now that's under construction.
Does the tunnel width change according to variations in demand from the adjacent intersection on intersecting corridors?
The tunnel duration that you see in the graphics I showed you, those times are set by the user. Now, all that really means is what InSync has to do is start the tunnel at the time that you specified. It's a must-be start time. Now, the local optimizer, depending on what it's seeing at the intersection with the platoon, it can start that platoon early, it can start the tunnel, or it can extend the tunnel later in time past what looks like the end of the tunnel on the time-space diagram, or it can even truncate the tunnel early if demand in the platoon goes to the intersection, there's nothing left in the platoon.
What do you have to do to configure InSync to deal with construction, or does it simply adapt to a construction event?
It depends on how much the construction affects your traffic. If you have a really heavy roadway that's 2 lanes in both directions and you close 1 lane, what you really need is at least doubling the amount of green time that you were given it before, because now you're funneling 2 times the volume of 1 lane, or your volume on the 2 lanes in the 1 lane. So with that in CentralSync, what you'll have to do is set up another configuration to handle that construction-related traffic. And you can run it just like we showed you how to set up a specific event configuration in the CentralSync schedule and specify a start and an end time.
How does InSync handle a typical downtown area where signals are likely to be under max PED recall conditions?
You cut out, did you say PED recall conditions?
Yes, sir.
All right, so With InSync, of course, you'll have to purchase the pedestrian intercept module to be able to interface with the pedestrian crossing, but InSync can be set up to automatically place PED calls over a certain amount of periods. So you could place a PED call every 30 seconds. So it pretty much acts like a PED recall. Now you'll have to take the PED recall out of your controller and let InSync handle the PED recall.
Can you explain why a pedestrian model is needed?
The pedestrian module is needed to be able to intercept the physical PED push out in the field. That will go to the InSync system before it even goes to the controller, and InSync will harbor that pedestrian push until it's ready to serve the associated vehicle phase within that period. At that time, then the InSync, the pedestrian intercept module, will place a call to the controller to service that PED when InSync is ready to serve that vehicle phase.
How does one obtain an InSync license? Do they have to purchase the license?
Well, there's no license involved with InSync. When you buy the InSync system, that comes with everything with CentralSync. CentralSync comes along with InSync when you purchase it, so there's no special licensing needed to run CentralSync on your computer as long as you have an InSync system.
Does the Global Optimizer have the ability to report how often when it adjusts a configuration?
Yes, there are logs where you can look at what point did the Global Optimizer change the period length during the day.
Do you have any videos of traffic at an InSync controlled intersection that show a shift in timing to clear an excessive queue?
Personally, I don't know if any videos exist. I think our marketing team would have a better idea of if any of those videos do exist, whether they're on our website or YouTube channel.
How exactly does emergency vehicle preemption work?
Well, I'm assuming that the emergency vehicle preemption, you're wondering how does InSync work with the emergency vehicle preemption? I mean, of course, you have to have the preemption hardware set up at your intersection, but InSync, it depends on the type of cabinet and the type of communication link between the controller and InSync. You may need an intercept module to listen to that preemption call. Now, it's important to keep in mind that InSync never intercepts a preemption call. The preemption goes directly from your preemption equipment to your controller. However, InSync can tap into that signal and just know when that signal's going on, when that call is going to the controller. So then InSync is able to back off and let the controller override InSync. And then, as I mentioned before, all InSync's doing is after the preemption call ends, it's just looking at a good time for the adaptive schedule to kick back in so it lines up with what the controller is doing in the field.
Dan, this is a multi-layer question. In the crossing arterial method, many high-volume arterials take on traffic from mid-block unsignalized intersections and business. If you cannot reduce green time of other arterials, you may delay the oncoming tunnel. How is this compensated in your method?
When you have a lot of mid-block traffic entering the corridor, what you're going to need to do in CentralSync is start the tunnel earlier in time by using the local offset and local duration features. So what you're doing is you're guaranteeing the start time of that tunnel downstream at an earlier time, so then you can start clearing out that queue early ahead of the platoon that's going to be traveling down the corridor. So then you'll have good flow with that platoon that comes from the upstream because you're starting the tunnel earlier and getting that queue started and going at speed.
What is the minimum and maximum increment in cycle time change from one cycle to the next cycle when traffic flows are constantly increasing?
There's no limit to how the optimizer changes its period. What I mean by that, you could have one configuration running a 90-second period, and all of a sudden you set at 2 p.m. that you want it to change to another configuration that runs a 200-second period, or that could be 5 seconds apart. It doesn't really matter. There's no limitation to how big of a jump NSYNC can make to go into another configuration.
Okay, Dan, thank you for answering those questions. Before you go, I'm going to send you a link through chat. Are you curious about getting to know more about funding? Funding expert Neil Blaze will be pulling back the veil on grant funding and showing some amazing insider secrets to getting the cash you need. Click the link for more details. Thanks for coming and have a great day.